So I'm going to be talking to you today about prototyping with Node.js and Firebase. IoT prototyping, of course, because hence the conference. But before I get into that, let me tell you a little bit about myself. Hi, I'm Jen. I'm a developer advocate, which means I get to come to events like this, and I get to help all of you build really cool stuff. And that's what this talk is about. My focus is primarily on Google Cloud Platform, so I guess the internet part of that Internet of Things. And I always love hearing from all of you, whether it's like questions about APIs or if you just want to share something cool that you've been building. So always feel free to hit me up on Twitter. I'm @mimingcodes. I'd love to hear from all of you. So before I dig into my stuff, let me ask all of you some questions. First of all, how many of you are professional electrical engineers? OK, I'm just going to apologize to all of you right now. I'm going to make a lot of simplifications and a lot of generalizations. We can talk about it later. But for now, just roll with it. How many of you know JavaScript better than C? That's what I like to hear. Because we're going to be doing, there's code in this talk, and it's all JavaScript. This is all about using what you have and doing cool stuff with it. And how many of you have like a Raspberry Pi or an Arduino Uno that's at your house, sitting on a shelf somewhere, gathering dust, all lonely? You had great plans to do something awesome with it, and it's just like sad. OK. This talk is all about using the skills and those boards you already have, including like the Edison and other boards you may have gotten recently, and doing cool stuff with it. So let's dig in. And here's my plan. First, I'm going to talk a little bit about electrical engineering stuff and kind of the context targeting at people with like mainly a web development background. Then I'm going to kind of switch over and talk about a recipe for IoT. This is my personal favorite recipe for a very specific use case, a recipe for building one of something. So it's like the bill of materials is a little more than something you'd put in production. It uses a little more batteries than you could if you optimized it, but it has the upside of being super easy to use, and you can get something working right away and focus on making your thing awesome. Then I'm going to prove to all of you that it's actually easy. I'm going to show you that by actually building something from scratch, live in front of you, and then writing all the code that makes it do Internet of Things stuff. And then I'll follow up with some silly demos of similar things using the same recipe. So first, electrical engineering for web devs. First thing we're going to talk about is signals. So when we build software, all of the stuff that makes up our software is represented by a couple of numbers, zeros and ones. At the end of the day, no matter what complex data structure you're using or lambdas, all that stuff, it boils down to zeros and ones that are somewhere in memory and through a CPU. And we have something kind of similar in kind of the electrical engineering domain. We have zeros and ones, which are represented on our dev boards as like a high and low voltage. In the case of like a board with 5-volt logic, like an Arduino Uno, your 1 bit is actually going, oh, there's actually backwards on the slide. The 1 bit's actually the high, the 5 volt, and the low value is 0 volt, also called ground. And this is what we're going to be moving around to make cool stuff happen. And so we have a 0 and a 1, so we have everything, right? That's everything we need in software to represent any of that complex structure. So we should be done, right? No. We need some more stuff. We need a couple more things, because the real world is about physical things like electrons moving around and conductors and all that stuff. So there's a lot of hazy zone, a lot more hazy zone than you're probably used to in software. And one of the kinds of signals we're going to read is an analog signal. And this is everything between that low state, that 0, and that 1. And this comes up a lot when you're reading from sensors that might be outputting stuff as kind of a range. And in the software, you end up reading this as a ratio of your precision. So like on a 0 to 1023 scale, you'd be reading that as some number between those boundaries. And that's great. So now we have zeros and ones and the stuff in the middle, right? So we should be set. One more thing, one more kind of signal that we're going to be dealing with, that we're going to be moving around. And that is PWM, which is short for pulse width modulation, which is a really big mouthful, but what it really means is analog output. So the analog signal on the top is the thing we will read from the outside world. So for a half value there, it would be like 2.5 volts. That'd be halfway. PWM works a little bit different. And it's actually a really big topic in itself. Like I could probably come up here and talk about it because people have written whole books on this topic. But essentially, it is analog output. And the difference is instead of like outputting 2.5 volts, what you do is you output 2.5 volts on average. So it's average over time. So you switch back and forth between the low and the high to make up that kind of analog signal. And the specific reason, it gets kind of complicated, but like the TLDR is that motors don't like half voltage. So this is the workaround we've developed, is we just go back and forth, and the motor will run about half as fast. It also works the same way for like light-emitting diodes. OK, so we've talked about signals. Let me show all of you some stuff. Let's do some show and tell. We're going to talk about the components. Components are a lot like Legos, except sometimes they dance. You can make them dance, and sometimes they catch on fire. But they're the little things you're going to take and put together to build your project. So I'm going to switch on over to my handy-dandy little projector thingamajig. I'm going to slide it over so it's a little less shadow. And I'm just going to walk through some of the different components we're going to use to build our stuff. I'm going to start with boards, because we might as well start with the most complicated thing first. This is probably familiar to most of you. This is an Arduino Uno. It is a microcontroller. Well, just this part. I'll talk about the other part later. So this is an Arduino Uno, and it is a board for, like, it's really good at reading from the outside world. It has a whole bunch of pins on these little things that you can plug sensors into, and it's really, really robust from kind of an electrical engineering standpoint. Like, you can do terrible things to this that would make other kinds of electronics sad, like, like accidentally plugging something into the wrong place, and it usually keeps working. So it's very resistant to the magic smoke problem. And it has a few different kinds of pins that I'm going to point out now. There's like these kind of like special pins that have like kind of like one that says 5E, which is like your reference 1, and a ground, which is your reference 0. It has some analog inputs that we'll use to read from like analog sensors, which will come up soon. And then it has a whole bunch of these digital input-output pins. And some of them have a tilde in front of them, which just means that you can use PWM. They can be enabled for PWM output. And that's great. So the Arduino is wonderful. It can interact with those sensors, but it does not have a very fast CPU as a result, which means we can't do a lot of the cool things we want to do for IoT, like transport layer security negotiations. So like SSL, HTTPS doesn't work very well on this chip. Like, there are ways to do it, but like internet and all that stuff is hard, because this thing doesn't have like an operating system. We're actually writing code on metal for the most part, like right on the CPU. It doesn't have file systems, not really, not like we're used to. It doesn't really have virtual memory. We're writing at a much lower level than we're comfortable with. But it's great. So we can plug our components into this and be happy. The next part of the recipe, next component I'd like to show you is this is a Raspberry Pi. Let me turn it so it's facing the right way. And this is a tiny little computer. It has a lot of the same features you'd find in like a laptop or a cell phone or some other higher powered computer that you're used to using. And what's great about this is you can like run a real operating system on it, like Linux, which gives you that virtual memory, that network stack, all that cool stuff we're used to that we've become comfortable with while we've been building for web development. And it has GPIO pins up at the top, so you can actually plug components into it directly, and they're pretty powerful. But I don't usually recommend people use it for their first project, because the Raspberry Pi is much less robust than like the Arduino. It's a little bit more finicky and a little bit more prone to breaking if you accidentally make it do something terrible. So set that aside for now. OK, let's talk about some of the more simple components. The simplest component you're probably going to deal with while building is a wire. So I'm going to bring one out and show you a little jumper wire. Jumper wires, we're going to be using a lot of these. What they do is use them to connect two things. And what you can use them to do is to move those volts around, move those electrons around. That's kind of the way you're going to move your data around. So there's a wire, which is great. We can attach them with soldering, but sometimes we don't want to solder, like at the very beginning of our project. And that's where this comes in handy. This is a breadboard. I actually found a transparent one, which is awesome. So how many of you are familiar with, have used breadboards before? Almost everyone, but a few people not. So I'm actually going to explain how they work. You can plug components and wires into them, and they have little like kind of clamp things here. And the way they work is like each one of these rows here is connected. So if we actually flip it over, we can see each one of these little sections is connected. So it just kind of like clamps different components together. So you can like play around before you solder things. And it also has these kind of rails on the side that go all the way up and down. And this is by custom used for power and ground, kind of like to have that reference 1 and reference 0 handy. And there's also kind of a trough in the middle, and that's just kind of a convention left over from a certain size of microchip. But like a lot of components are built to take advantage of that trough. And that is a breadboard. Oh yeah, and like breadboards are great while you're building things, but eventually you're going to want to like actually take it out into the world. And if you take a project on a breadboard and shake it, all of your components fall off and you're sad. Which is why there are these wonderful things out there called perf board, which just stands for perforated board. It comes in lots of different kinds. Some where you actually like it's just a bunch of little pieces of metal in a grid that you like connect with solder. But they also have kinds that look just like tiny breadboards, which are my favorite because I can just take whatever design I had on my mini breadboard, and I can just copy it over, and I don't have to think a lot about evaluating that circuit again, which is great. I love not thinking about something, so I can think about like my project. Okay, so we have things that are, one more kind of like wiry component that's going to come up a lot. This is a resistor. A resistor is kind of like a really terrible wire, which you wouldn't think is useful, but it turns out it's actually really, really useful. It comes up a lot, and we're going to be using them a little further on in the talk. And they come in a whole bunch of different values that are just, you can actually learn the color code, the band code. But I tend to just kind of keep them in little bags that describe what they are, so I don't have to, because I don't like thinking about things I don't want to think about. There's a whole bunch of different kinds of resistors, and you can build very sophisticated things with just them. But for the purpose of this talk and your beginning project, all you really need to know is that there's 10K ohm resistors. They exist, and they're all you really need for right now. 10 kilo ohm. Okay, some more components. This is a tiny button. It is a push button. It has 2 pins that stick out of the side. And when you leave it alone, what happens is it does, when you leave it alone, no data is moving across it. So it just kind of is open in that case. And when you push it down to close it, when you push the button and feel the click, the 2 little wires are connected. And it allows electrons to move from one side to the other. So we will be using that as this very simple digital input. Another simple digital device is a light-emitting diode. Here is a nice yellow LED. LEDs are little light bulbs. If there is a 0 on one side and a 1 on the other side, it turns on. If the value is the same on both sides, it does not turn on. It is directional, so you have to have the 1 on the side that's longer and a 0 on the side that is shorter for it to turn on. And that's a really wonderful digital output, super simple. And I mentioned analog and PWM, so I'm going to show you a couple other components. This is what's called a potentiometer. It is a little dial, and it has 3 pins on it, and it's kind of cool because you put a reference 1 on one side, 5 volt, you put ground on the other side, and then the middle pin will tell you how far along the dial you have gone. So it gives you an analog input that you can read from and do cool stuff with, like controlling analog components, like this servo motor. And a servo motor is kind of like the opposite of a potentiometer. It has a little arm that moves. Generally, you don't want to play with them while they're off like this, but I want to show you. It's also a 3-pin device, and if you give it a ground on one side, voltage on the other, and then a PWM input in the middle, it'll go to the ratio of that. So you can actually do an analog input on a potentiometer, turn it, and then make the servo motor move by converting that to PWM and outputting it. Cool, okay. So we did show and tell. We talked about some components. Let's go back to slides. Boop. So I showed you a bunch of stuff. Now for the recipe. That's kind of like the list of ingredients we can pull from. The recipe I use for all of kind of like the first time I build a project is this. I start with all those components. So I figure out what I want to build and what components I need to solve that problem. If I need something to move, there might be servo motors, Legos, who knows. There might be sensors, wires, there might be chips that do something, like IMUs, like sensors like that. Motors, maybe. Once I have all my components together, what I do is I connect those to an Arduino Uno is usually the first board I will use. Because, like I said, it's great at handling the real world and all of the kind of quirks of it. And then I programmed that Arduino with a special sketch, a special program called Fermata. And Fermata allows me to plug it into a Raspberry Pi over USB and then kind of like offload all of the work of controlling the components, which is great. Because now I can actually control all the stuff, all those components, via the Arduino from my real operating system on the Raspberry Pi. On the Raspberry Pi, I use Node.js and my favorite Node.js library, Johnny 5. And you'll see why it's awesome, but it is a Node.js library for sending Fermata signals and controlling those components. And now at this point, we have a thing. So we have JavaScript running on a Raspberry Pi, and it can move things around. And we need that last ingredient, internet. For this situation, I use Firebase. So let's dig a little bit more into a couple of those components. First, let's take a little deeper look at Johnny 5. So I'm just going to go to, if you just web search for Johnny 5, there's official documentation. There's also the older GitHub README. Make that a little bigger. And it is awesome, and I will tell you why it's awesome. There's actually a lot of libraries out there for doing like Fermata control from Node, so I recommend give them all a try. But Johnny 5 is my favorite, and the reason is because this documentation is amazing. Not only does it have a huge picture of a robot like doing that, which is pretty cool, especially if you remember the movie. Does anyone remember the movie? Yay! Okay. But the cool part is you scroll on down, and there's like a list of the different components you might want in a system. Like, for example, let's say we want a button. We want a button, OK, so I don't really need to know anything. I just make my breadboard look like that. And then it will work. And then accompanying that diagram is the code that makes that diagram work. So then I take this code and I paste it into a file, and I Node run it, and it's just working. And the cool thing is you can actually string together a bunch of those things, because we might want more than a button. Like I can go find some other sensor, like, I don't know, how about a LiDAR, which stands for laser radar? And I can copy that picture again, change the pins so none of them conflict, because I can remember numbers to move around. And then I just paste this code into the same program, and I can build up like a very rough like hello world of all these components just by copying and pasting and copying pictures, which is awesome, because then I can think more about like the details of how I want my thing to work and how I want people to use it. And that is why Johnny 5 is awesome. And there's just so many components, LCDs, buttons, motors, all sorts of stuff, and all of them have very similar format for documentation. That's why Johnny 5 is awesome. All right, let's talk a little bit about another one of those, which was Firebase. So one of the ways I look at Firebase is it's kind of a bag of goodies to make app dev easier. And how many of you have used Firebase before? Ooh, a bunch of people. OK. So Firebase is like it's a kind of a bag of goodies, and it has a whole bunch of different components, which you could use independently, but fit very well together. And it handles things like synchronizing real-time data, handling network disconnects, like offline time, and all that kind of stuff. It also has like static file hosting, because a lot of people write Firebase apps that just use JavaScript and JavaScript and HTML. And it also handles we have a whole bunch of authentication helpers, because how many of you have implemented OAuth before? Was it fun? No one ever said, oh, someone said yes, but I don't know if it was serious. OAuth can be kind of a little bit of a headache. So Firebase has libraries that make that a whole lot easier, which is awesome. But we're only going to be talking about one of those components for this recipe, just the real-time database. And the Firebase real-time database is, I kind of think of it as a big ball of JSON in the sky. So if I can take all of the data I need for my project, whether it be a mobile app or an IoT project, if I can represent as a hierarchical data structure, JSON, then I can stick it up in Firebase using these set and push methods. And then my devices or my apps that work with my devices can choose to listen to, you can subscribe to either nodes, subtrees, queries against subtrees. And what will happen is Firebase will automatically make callbacks on my mobile app or other code that relates to my IoT device, which makes it so much easier, which is awesome. And I could tell you more about it, but why don't we actually just look at some of the Firebase stuff in action? So, boop. Oh, no, it's freaking out a little bit. Let me reload that. It doesn't like being in a tab. All the events replay. So here's an example. This is the Muni buses. Did anyone take a bus or subway since they've been in San Francisco, since they came in? So was it on time? So this is an example of real-time data that you care about being real-time, where your bus is right now. Because you don't care where the bus was 2 hours ago, or where it was yesterday, or aggregated data from a long time ago. If you're sitting at a bus stop and you're cold, you care about where the bus is right now and why isn't it where you are. And here's actually all of the Muni buses, the municipal bus system in San Francisco, right around us. And this is where they actually are as of 100 milliseconds ago. Being San Francisco, you can tell that most of them are stopped. This is real data. Like the example's real, the buses are just not moving, probably because it's getting on into rush hour. One game I like to play is looking for clusters of buses that are the same. Like how many 5s can I find right next to each other? It's like, that's where they are. They're all having a party. OK, so here's one other example of real-time data, which is real-time collaboration, like collaborating on Google Docs comments. I'm going to take a little risk here. This is an interactive slide. You can pull out your mobile device or laptop. If you go to firesketch.firebaseapp.com, we can draw a dinosaur together. So I'm going to start, and if anyone wants to join in. Boop. Oh, someone's helping. Who's helping? Is it fast? Yeah. Cool, OK. So yeah, you can see a whole bunch of people are joining in. And thank you for being nice. This is a risk to have people draw on stage. You never know what can happen. So switching back to my keynote slides. So that's just a couple examples of what real-time data is, why it's cool, and I guess you can kind of get an idea of like how it relates to IoT projects. Because we often care about interacting. If we hit the button, we want the lights to turn off now, not in an hour. So here's some of the code that you use to interact with Firebase. We have, if you want to write to Firebase, the first thing you do is you connect to Firebase. You connect to Firebase by just installing the client library, and then just attaching to Firebase, which all Firebases are identified by a URL, and all locations in them are also URLs. You can just use path segments to work your way down that JSON blob. If you want to write data, we have a few different methods, but the simplest is set. You take your reference to a location in Firebase, and you call set. And then you pass it text, numbers, JSON, anything that could be in JSON, including another JSON tree. When you want to read data, this is the part that gets cool, you just attach a listener. Just like you would attach a listener to a button on a web page, except this is a listener to the internet. And when that location or that query changes in Firebase, we'll automatically call your code. And what's cool about this kind of really simple interface is that the Firebase client libraries handle like local caching, they handle like threading, all that stuff that's kind of a pain sometimes. It also handles things like going between online and offline states. OK, let's build some stuff. So now we have all of our recipe components ready to go. Let's actually build something. And we are going to build Hello World of Electronics. How does that sound? Does anyone know what Hello World of Electronics is? Blinky light. It is a blinky light. Yes, we are going to have a button, and we are going to have an LED. And when we hit the button, we're going to make the LED turn on. But with one special twist, we're going to be sending data through the internet to do that. Because why not? So, like I said, I'm just going to copy what Johnny 5 shows in that picture. So I'm going to go over to Johnny 5, because this is the easiest way to live code. You just have it pre-done and copy and paste. So we're going to go over to button. And what does button have? The first thing button has is it has some wires moving across, and then a button. So I'm just going to drag that down into the corner. So you can see a reference. Actually, I'll just leave this up for full screen. So first thing we're going to do is we're going to get some jumper wires, and we're going to kind of move that reference 0 and reference 1 over. And so there's a little ground pin here. I'm going to stick a blue cable in that and copy it over with the wire, over to the little minus rail. Then we're going to take the 5 volt, which is our reference 1, and we're going to use the wire to send it over to the little red rail, which is unlike the picture. The picture is backwards for some reason. They decided blue should be on. But in any case, the next thing we're going to do is we're going to take our button and stick it into the breadboard. This is a regular push button. I put some feet on so it actually connects to the breadboard well. And we're going to grab some jumper wires. And first thing we're going to do is we're going to use purple. Grab a purple wire. And we're going to make one pin, the red. So we're going to connect the red side to one of the button pins. And then we're going to connect the other one to one of the digital reads. We can use any of them. So I will use a red wire, and we're going to read from, why not, pin 4. 4 sounds good. So now what will happen is, so we have a button. It looks like it should work at this point, because like we hit the button, right? And then it copies that 5 volt, that reference 1, over to that pin, and it should be great. But there was actually something extra in this. There was a resistor there that went to ground. And this is where kind of that like real-world physics stuff comes in. This is the case where you might need an awful wire. Because like our button, like it copies data, but only when, or copies state, but only when the button is pushed, when it's open. So when the button is pushed, everything is fine. The 5 volt is coming across, it's going across, and it's getting sent over to, oh, that jumper wire broke. I'll replace it. It sends it over to the input, and we read it. But when we let go, it opens up, and it's no longer moving any state, which is bad because we have some trapped electrons that are hanging out there causing trouble. And how that'll manifest on your project is you're going to see the thing kind of bounce back and forth between 1 and 0, which is no fun because it's confusing. So okay, so that's fixed. So what we're going to do is we're going to use a pull-down resistor, is what it's called. So we're going to plug it into the side we're reading from, and then we're going to put that into the ground. And what this pull-down resistor does is if the button is pressed, it doesn't do anything. Like the reference 1 still gets copied, and the input reads it, and it's fine. But when you let go, it kind of drains out that excess charge and makes our circuit work. It pulls it back down to 0. OK, so we have a very simple circuit. Let's do some live coding now. And by that, I mean copy and paste. So I'm going to grab all of this. I'm going to open up my terminal. I'm going to open up VI, the only text editor or IDE the world will ever need. Paste in off the internet. Let's delete some of this extra stuff. There's a lot of stuff in here we don't actually need. Like there's some REPL stuff, which we were not going to be using that. And we have a very simple program now. But before we can use it, we have to. Now will be a true test of the conference Wi-Fi. Live installing. Yeah, because it was an empty directory before I started, as you can see. Cool, OK, so it installed. Yay! And here's our program. I didn't actually change anything. I should probably change the pin number. We actually plugged it into, what was it, pin 4. Changed that from 2 to 4. And then Node. We're going to run Node, awesome.js. Oh, I haven't plugged it in. Plugging it in would help. With a USB cable. Oh yeah, so one thing you're seeing here is I'm actually plugging into my laptop instead of a Raspberry Pi, and that's because, as I mentioned, a Raspberry Pi is like a very similar to a very small computer. So you can use, while you're doing development, you can use your computer instead, which is great, because it works a lot better, because it has a keyboard on it and stuff. And then later, when you want to actually take it out into the world, you can copy your program to the Raspberry Pi, and everything is happy. OK. So we should see something when we hit the button down. It should say down, and we let go. It should say up. So we have our hello world in terms we have a button that goes up and down. Yay. OK. Let's go copy in another part of that. We want to have a little LED that turns on and off when we hit the button. So let's go ahead and do that, and then we will refactor internet into it, the best kind of refactoring. So we're going to search the page for the thing we want. We want a LED. So we're going to go over to LED. And it says take an LED, and I'm going to grab one. I'm going to grab a little yellow LED. And their circuit diagram is very simple. They're just plugging it into the board. I'm just going to move that over to the breadboard, and then we're going to copy this code. So what I'm doing is I'm remembering which pin is long, because that's the one that has to be warm, has to go to the high voltage. Then I'm going to take the reference low from that little rail, and I'm going to connect it with the jumper wire. And then I'm going to use one of the digital inputs, or one of the digital outputs from the Arduino to make the LED light up or dim. So I'll grab a brown wire again. Should bring more colors. And we'll use pin 12. So now if pin 12 is set to high state, to 1, we're going to have a 1 on one side, and we have a 0 that's already there, and the LED will turn on. If it is not, the LED will stay off, because there'll be 0 on both sides, and no charge will move, and no LED will turn on. So let's go ahead, and this one is pretty simple. We just var an LED. So we're going to go back over to our awesome text editor. We're going to make an LED. And it was on 13 in the diagram, but we changed it to 12 because we like living on the edge. And to turn it on and off, on, and LED.on and off. So when we push it down, the LED will turn on. When we pick it up, the LED will turn off. So we'll run that code. We'll see our little thingy down there. Put this up here. Shrink this a little bit. Shrink you. Now our program is running, so when we hit the button, the LED turns on. Yay! OK. So now we've pretty much finished the thing part of our Internet of Things. Hello, world. Let's add some internet. But actually, this is a great point to kind of like take a breath when you're building something, because now you probably don't have to move around too much of the electronics, and you can switch back to web dev mode, put our JavaScript hacker hat on. So we're going to add internet, and I said we do Firebase. So let's add some Firebase. So I'm going to go to firebase.com, because I'm going to continue the live code by copying and pasting, because I'm just going to go and copy stuff out of the quick start. So we're doing the internet, we're building for the Internet of Things, but we're going to go to the web quick start because it's the one with the JavaScript in it, because we're using Node.js. The first thing we're going to have to do is install Firebase. That was fast. That was awesome. We're going to have to get the Firebase. See if the little copy thing works today. And the next thing we're going to do is just kind of walk on through it. So now we have the Firebase client there. We're going to connect to our Firebase, which we're going to do right around the place we instantiate those buttons. We're going to change it to firebutton.firebase.io.com. And then I'm going to do a little trick. If you just add -demo to the end of a Firebase domain, it becomes a demo Firebase, which means you don't even need an account to create it. But please don't launch production apps on it, like your data is going to get deleted at random, because it's for demos. Then I'm going to put a path on there, just in case I want to use that demo Firebase for more things like many buttons. And we're going to go to so this location. One cool thing about Firebase is if you want to see what's in there in your web browser, we can just drop it in there, and we can see it in this Firebase console. So I'm going to remove that node. Just going to take a look at the whole Firebase. I just cleared stuff out because I practiced, so there was data in there already. No, now it's empty, like you got to it for real the first time. Then the next thing we're going to do is we want to write that button state to the internet. So we're going to go right here to writing data, which is very conveniently the next step in the quick start. What are the odds of that? So we are not writing complex JSON. We're going to write something very simple. We're just going to write down when it's down, and we're going to write, not that, up when it goes up. So we're just going to write that state to the Firebase. So now we have a write-only button. Let's give it a kick and see if it works. So we have our little program there. I'm going to split the screen more times, because why not? We have our little Firebase viewer here. We have our button up there. I started up the Node script. Let's see what happens when we hit the button. So we hit the button, and then when we press it down, it writes down and up to the Firebase out on the internet. So now we have made the very, very, very minimal Internet of Things. We have a thing that changes the internet when you touch it. Yay! But that's not quite what we wanted yet. We wanted to turn the LED on and off via the internet, right? So rather than turn it on and off here, why don't we read from Firebase to turn it on and off? So we're going to go back on over to the quick start. We're going to go to the next step, reading data. It's like this is rehearsed. And we're going to paste in the reading data step. And we don't want to do an alert, though. And we also don't want to read these things. OK, so this just like goes into another subpath. We just want to read a reference. And here's like a Firebase callback. So the way it works is I give it a function that'll get called whenever the value changes at that location. And it's going to send me a snapshot, which contains like a whole bunch of metadata. It's like an immutable representation of the state of the data at the time it got called. All we really want is the value, because this is a silly project. And so we have our button state. We want to do if down. If the button is down, turn the LED on, else. So what this does is whenever the state of the button in Firebase changes, this function will get called. Oh, do I have a? Oh, is it outside the if? Oh, yeah, I do. Thank you. Live coding with audience help. It's like pair programming, but crazy more. OK, so when the button goes down, so this will get called whenever the state changes, and then I'll just extract the value, and then I'll just do a little if statement on it. See if it works. So I have my Firebase viewer over here. I'll drag that back down so we can see. I have the camera, the button. OK, and it's running. So when I hit the button down, it changes the internet, and then the internet changes the thing. So now we've made the full loop. And what's kind of cool is I can go to the internet, and I can just change it directly, all hacker-like. And it changes the thing from my web browser. So we have now done our hello world, minimal Internet of Things thing. So that means it is time for silly demos, right? Let's do some silly demos. So there's code we already saw. We built something. OK, silly demos. So sillier than even this, because let me actually turn my Firebase back. Let me set that back to up. The LED turned off. OK. Where was my? There we go. OK, so silly demos. One thing that's kind of cool is if you take multiple of these things and you combine them. So I have maybe prepared like a cooking show, another one of these up here. I can actually use it like a telegraph, like the most overly complicated, silly telegraph ever made, which is great. And actually, we can do it like if someone wants to press it from the audience, you can press that every once in a while, and we can actually play a little. We can actually communicate in Morse code, which is cool because we're going through like a server in Texas right now, which is awesome. We're also on 2 different Wi-Fi networks. That is actually on a cellular phone tether, and this is actually on the conference Wi-Fi. And it's still really fast, which is really cool. And you can do more things with this. Like you can interact with anything that supports a Firebase client, like my slide deck. So if someone would hit the button, you can do things like, hopefully, rickroll my slides. But it did not seem to work today. Rick did not want to come out. Oh, there it goes. It just took a little while to load. So you can do things like rickroll your slide deck from the internet, which is awesome. And here's another example of something you can do, another silly demo. Remember those potentiometers? I grabbed a couple, and I'm like, what's the simplest thing I can build with potentiometers? I built an Etch-a-Sketch. So I can actually draw on my little JavaScript whiteboard. And what's cool about this is I think this is like 60 lines of code, and that whiteboard is under 100 lines of code also. So like these are things you can seriously hack out in like under an hour, which is great because then like once you've built your thing, you can go take it into the world, put it in somebody's hands, and then you can start to like do user testing and like find out the viability of your project before you have someone like crank out 1,000 PCBs for you, which like costs money and is hard to undo. OK, so we have some silly demos. So some parting words while people play with the button. First of all, wasn't that easy? Was that easier than you thought it would be? OK, that's what I like to hear. Because like this stuff should be easy and it should be fun. And this is the most fun way I've found to do it. The other piece of advice is like there's always new boards and new cool things coming out. And one thing I found that helps me a lot, kind of focus and actually get products done, is I let the projects guide me. So like when a new board comes out, I'll note it that it's there, and I'll wait to buy it till later, so it doesn't sit there on my shelf and gather dust. Instead, I think of a cool project I want to build, like an Etch-a-Sketch, and then I make a shopping list and let that guide me and let that determine which board I'm going to use. And in Dowd, I usually use boards I already have lying around, because rarely do you need the newest, shiniest, fastest board, especially for like projects like these. The next thing I like to encourage you to do is experiment. Like, do silly things, like try them out. Especially if you have the parts lying around, just throw them together and see what happens. And don't be too afraid about things breaking, about things catching on fire, which is kind of into the next one, is while you do this kind of hacking, things are going to break. You are going to discover the magic blue smoke that when it comes out, stuff stops working, doesn't go back in. Celebrate that. Like, it's going to happen. It's OK. Learn from it, and try not to burn up your next board the same way. As it turns out, like motors, like when they spin, they generate power. It's like, whoa, I never thought of that, but it makes sense. Now I need a new board. That's OK. Oh yeah, finally, now go build cool stuff. I know almost all of you have at least one board to play with. And so go build some cool stuff and like tell us about it. Show it to us. Like, get out there on the internet and like share the things you're building, because like it's such a great community of makers right now, which is so much fun. It's such a great time to do this. So thank you. That's it. And now we have like over 15 minutes for questions. And there are actually mics around if you're present and like to ask a question. Otherwise, I'm going to open the floor up to questions. No questions from anyone? Oh, there's a question.
Can you just tell me where you source and get a lot of your sensors, or good websites where you find like good sensors at fair value?
So the question was about where I buy my stuff, my sensors, my components, all that kind of stuff. There's a whole bunch out there, like DF Robot, and but like, I think my favorite one is Adafruit. Adafruit.com is awesome because not only do they make great stuff, but like Johnny 5, like their documentation is awesome. They have this whole like Adafruit learning system, and then tons of other like social media and videos out there that help you build all this stuff and like make it a lot less intimidating than reading spec sheets. Although they have the data sheets too. They're actually very good about linking to those docs too. So they make it easy and fun, which is awesome.
Two questions. First one is looking at the simple schematic you had with the pull to ground and so forth. I spent an hour not knowing that, for those of us who aren't EEs, where can we learn easy, simple stuff like that we need to know to make these simple circuits?
So where can you learn the minimum amount of electrical engineering to get by? Honestly, the best place I found is the Johnny 5 documentation. So I either find the Johnny 5 documentation, or if it's something more sophisticated, like Adafruit actually, with all of their components, there's a lot of tutorials that go along with them they go into great detail on like why you need to put a capacitor across power and ground on your big LED projects. And they explain this in great detail, and they back it up with videos. Beyond that, if you're doing something more esoteric or a little more challenging where you need to go a little deeper into stuff, YouTube, because you actually see people putting it together under the camera. Which is a long way. It's a lot more than just pictures of schematics. They usually explain it while they're building it too.
And the second question is, this was great to see with Arduinos and Raspberry Pis and all of these components. What about the components that we have in our toolboxes? What about our Edison? What about Brillo and Weave? How do we map what you just showed us to all of that?
Great question. So one thing that's really cool about Johnny 5's architecture is they decoupled all the board logic from the abstracted sensor interfaces, which means if I go to the official Johnny 5 documentation, which is now on Johnny 5 IO, which is pretty, you can see pictures of all the boards it works with. And I'm pretty sure the Edison is in there. Oh yeah, there it is. There's the Edison. So a lot of different boards in there. I'm not sure the other one's in there because I forgot what the name of the board was. But the Snapdragon? OK, well, I'm not as familiar with that board, so I will leave that as an exercise to all of you. Dragon board? I don't know if it's in there, and I can't search the page with text. But click around, and if if Johnny 5 does not work, I can guarantee you there's some other Formata library that works. Because every time I've looked, like, I wonder if there's a Formata library for Ruby that has good community support. And like, there's always more than one option, which is great. Because then I can program in Ruby and build this stuff, which is fun sometimes too. Any other questions? Oh, I see one with the mic.
How come when you plugged in the LED, it didn't short without the resistor? Because you connected it straight to ground. Like, wouldn't there be too much current and would like destroy the LED bulb?
Oh, so the question was, why did the LED not get angry because I put 5 volts across the LED, and I kind of did a trick. Because LEDs come in different colors, and it's one of kind of the nasty complexities, is different colors, whether it be yellow or red or blue or green, have different ranges of voltages they're willing to accept. And one pitfall, just to prevent you from your first fire incident, is 5-volt Arduino Uno and a red volt LED do not get along like that. The red one it'll light up briefly, and then it will never light up again. That's because the maximum voltage is less than 5. So what you can do is you can take that resistor and you just put them in line together. So you connect, like for example, you connect the LED to ground or to the digital pin with the resistor in line. I use a yellow LED because it will accept 5 volts without catching on fire, and that was easier to do for the talk. But great question. Yes, the components all have their own little quirks, and things as simple as color can actually change a lot.
I have one more question. You said that the fan generates power. Does that have any effect on your circuit?
Oh, so I briefly mentioned that one of the ways I discovered when I blew up a board was I plugged a motor directly into it. And the motor was small enough that the current draw didn't burn out the board, which can also do it, which is why you usually want to use like a transistor to move a motor. But what happened is that the motor was spinning, and there was the load on the motor. So when I stopped sending electricity to the motor kept spinning. And it's what's called, I think, phantom power or something like that. What happened is when a motor is spinning and it doesn't have electricity coming in, it becomes a generator. So it started feeding electricity back into my pins, and then it burned out my board. Which I've actually done in an Arduino before just to see if it would burn it up, and it actually didn't. The Arduino Uno did fine, even with tiny motors spinning, which was cool. It's like, I'm going to try and break this thing. I can't. Yay. But that's just something else to be aware of. You can use transistors, or you can use a diode. Like the diagrams all over the internet will give you that particular tip.
Hey.
Hello.
Is that possible to make that work without the Raspberry Pi? I don't know, with an Arduino Wi-Fi shield or something?
Is it possible to do this with cutting the Raspberry Pi out and just doing an Arduino shield? And the answer is kind of. So technically, yes, you can build all this whole thing only in Arduino, and there's libraries to do the Wi-Fi. You might need a more powerful Arduino to do the TLS negotiation before it times out. You can technically do it, but like I said, you don't have, when you're coding right on metal, you lose things that you're used to having, like an internet stack. So you're actually building the packets by hand each time, whether you're doing it or a library is doing it. You also don't really have threading. So like you have to wait for that data to come on the wire. So it ends up being like you end up diving way too deep into protocols, way too deep on the low-level stuff. Why do that? Like operating systems already solved that a long time ago. Like take advantage of those. Then later, like this is great for building one of something. When you go into production and like your Kickstarter is funded and it's super successful and you need to build 1,000, that's when you worry about that part. Because then you can save like tons of power and stuff, and it's awesome. Because, yeah. See one more question coming around.
Yeah, you mentioned some word that I didn't hear in regards to Johnny 5, like a chroma language or something. So what is Johnny 5, and what is the name of its Ruby counterpart that you mentioned?
A Ruby counterpart. Yeah, so there are a whole bunch of different Fermata libraries. You can actually just web search for Fermata library.
I don't know what word you're saying.
Oh, Fermata. So this is the word called Fermata. Actually, I'll show you Fermata real quick. I have time to show you. So Fermata, so like when I first started doing electronics and I wanted to do like a computer attached to an Arduino, I was like, I'm going to build this protocol language for moving this stuff around so I can just control it from my higher level programming language on the computer side. And then I did some searching and I started building it. And about halfway through, I realized not only had it already been written, it is packaged with the Arduino thing. So like the Arduino IDE has a section under samples called Fermata. And there are a whole bunch of different Fermatas. Standard Fermata is the standard one. And you open it up, and it's a sketch. And it's this very mature protocol that's been around for a long time, very polished, super easy to understand, and super easy to extend. And you can just like flash your board with it. It's uploading right now. And it's not working because Johnny 5 is still running. Yeah, and so once you get Fermata on your board, which you can just use the Arduino IDE to do, then you can go find a library. Like you can just search for like language and Fermata. And Arduino Fermata on Ruby. And it's another beautiful library. that I've used a little bit, and it worked really well. And what's cool is you can go back to Johnny 5 and use like their pictures and then just like translate the code over to the other libraries. But yes, fermata is the code, is the word. Any other questions? Okay, well, if you ever have any questions or you want to show me something cool, like feel free to grab me or tweet at me or whatever you see me. I'm around sometimes. I'd love to see what you all are up to, and thanks a lot for coming to my talk.